Good afternoon, everybody. Welcome and thank you for joining us for the 2020 and 2021 medal talks for the Canadian Association of Physicists. We will move on to our second talk of the afternoon, and I'll invite Vincent to turn on his camera, and would like to acknowledge the 2021 CAP Medal for Outstanding Achievement in Industrial and Applied Physics, which has been awarded to Vincent Tabard-Cossa from the University of Ottawa to recognize his innovative contribution to physics by developing a new nanopore fabrication technique. Nanopores can electrically detect individual molecules like DNA and proteins and are finding applications in next generation diagnostics, sequencing, and data storage devices. Dr. Tabard-Cossa's groundbreaking controlled breakdown method of nanopore fabrication simplifies and replaces a previously cumbersome and expensive process, enabling scalable, low-cost fabrication of solid-state nanopores at sub-nanometer scale. So I would like to invite Vincent to share his slides and give us his CAP Medal talk. Welcome and congratulations, Vincent.
Okay, well, thank you very much for the very kind introduction, and thank you to the CAP community for this recognition. I'm thrilled to be here today to tell you about some of the work of my lab that at the University of Ottawa, where we've been developing, discovering this novel fabrication method to make solid-state nanopores, and also translating this method into an innovative technology. But before I start, I really need to confess that the people responsible for the work I'm going to show you today is this a group of amazingly talented and diverse group of graduate students, postdoc, and undergraduate students that have worked with me to discover this method, but also transform it into a technology that is now being used in many labs around the world. So what are we talking about when we talk about nanopores? So a nanopore is essentially a small hole in a thin membrane about the size of a molecule. And if you insert that membrane containing a pore inside a liquid solution, and if the pore is the only conductive path between those two sides, and if you apply an electric potential across it, you can drive the motion of ions. And whoops, sorry, these ions are then, you can then measure a current responsible as a result of the movement of these ions. And let's get back to this now. All right. So these ions, sorry, from this motion, sorry, so from measuring of the current, you can get information about the size of these pores. And basically, you can get dimensions of the diameter of the pore. And this first term here in my equation is the bulk resistance of this channel, basically transversing this membrane. And then the second term, this 1/d term, tells you information about how the electric field is outside the pore, sort of decays a bit like a point charge decaying outside the pore. And it's that decaying electric field that can be used to capture diffusing molecules and beat their Brownian motion and bring them in and confine them inside the pore so that you can detect them electrically. And here you see this blockage in the electrical signal, which is basically a measurement of the molecule when it's confined in the pore. And it's an electrical measurement of that molecule, and it's proportional to the size of the molecule. And so these nanopores are finding applications in a number of fields, including clinical diagnostics, where you want to electrically detect biomarkers indicative of disease, and this could be proteins, DNA, RNA. You can count them one at a time. There's also been, over the last 5-6 years, tremendous development of nanopore sequencing that basically our nanopores are allowing long-read electrical detection of the bases on the DNA strand. And then on synthetic polymers, synthetic DNA, or some other type of synthetic polymers, you can also encode information, digital information on molecules and use a nanopore to decode that digital information. The nanopores that I'm talking about, they come in different flavors. For the most part, you have these biological pores. that are these protein pores that come from different organisms, and you can extract them and mutate them to behave the way you want for your particular applications. And these biological pores here have feature sizes that are making them really ideal for DNA sequencing applications. And so the limiting aperture of these pores is so small that you've got at the most smallest constriction, you've got just about 1.4 nanometer diameter. And this allows, is one of the reasons that allows for these pores to be able to sequence DNA. It's this exquisite resolution that these pores have at the really almost atomic scale. And about 20 years ago, physicists decided to try to mimic these biological systems and decided to fabricate on these solid state material, try to fabricate pores that had similar size features. So what you're seeing on the left here is a thin membrane made out of silicon nitride in this gold color, supported by a support chip made out of silicon. And this, you can imagine, can be made on the wafer scale. And the idea is to try to make a membrane that is essentially as thin as these nanopores, or a few nanometers, and you make pores, these biological pores, and you make a pore in that membrane also of those dimensions, so a few nanometers wide. And you want to control it precisely so that you can really tune it to be fit to the molecule of interest. And the ideas of moving to the solid state platform is that you have this easier propensity to be able to integrate them with CMOS electronics and microfluidics technologies. But it was quickly realized that it's a pretty complicated challenge to drill nanopores into Sculpt Matter at this nanometer scale, at the single nanometer scale of 1 or 2 nanometers, and to control the size of these features with almost atomic precision. And so when I entered this field back about 15 years ago, the way to make pores was to use a transmission electron microscope. And instead of having a diffuse beam to image your membrane or image your sample, you focus the beam down to a tiny little spot, and you would essentially use your electron beam, energetic electron beam, to sputter atoms away and to create a small feature of pore into that membrane by looking at the phosphorescent screen and looking at flickers to tell you that the pore has been formed. A very manual and labor-intensive approach using quite a complex instrument. And there are other tools out there since then that have been developed to do this, whether it's E-beam or electron beam lithography. That's not a really good technique to make features below 10 nanometers. And there's been progress and focused on beam methods to really sculpt material to even smaller dimensions. But again, to do things at the 1 to 10 nanometer scale with angstrom precision, none of these tools really were able to make this work. So in addition to the fact that they're complicated, they didn't have the resolution to do it. So what happened is that at the University of Ottawa, we then came up with a way to fabricate nanopores that use the simple idea of controlling the dielectric breakdown of these insulating membranes. So what we did is we applied a voltage across these membrane in solution, and to generate an electric field high enough to create a breakdown event, a dielectric breakdown event, that leave behind a single hole that we can then enlarge with atomic precision using a series of voltage pulses. And so as you may kind of realize, we now have a much simpler technique that replaces your complicated instruments that uses ion beam, high energies of beams to actually sculpt matter with a simple electrical circuit that uses off-the-shelf component that can even be battery operated, simply to apply a voltage across our membrane and to control the defects the damage that we do during this breakdown, simply with a feedback system that measures the current to that membrane. So with the rest of my presentation today, I'll mention the physics of how we make nanopores using this controlled breakdown technique. And over the years, we've been filing with my students 6 patents on this technology, and published about 10 papers describing the various mechanisms of how these nanopores are formed with these membranes. So imagine that you start with your intact membrane. It's a thin piece of silicon nitride supported by the silicon chip, and you immerse that in your favorite solution of electrolytes. So here's a simple salt solution of KCl, and you place electrodes, microscopic electrodes, far away from the membrane, and you apply potential across that. Because your membrane is an insulator, you don't expect it to measure any current when you apply this potential. And that is true until you reach a certain level of electric field across this membrane. And here we estimate the electric field by simply dividing the voltage we apply by the membrane thickness. And because our membranes are 10 or 30 nanometer thick, we just need to apply 1 to 10 volts to create electric fields that are quite high, between 0.1 and 1 volt per nanometer. And as you can see here from the figure on the right, we can generate some leakage current through these membranes by applying these high electric fields. And that leakage current is reversible. So if we go back to low voltages, that leakage current disappears. And so no physical damage happens. And because there's no intrinsic pinholes or defect in the membrane, holes in the membrane initially, there's no current at low voltages. But if you start sustaining this electric field, you do see a leakage current going through this. But these membranes are a bit too thick for that current to be direct quantum mechanical tunneling. So what you have instead here is a redox reaction that inject charges in the membrane, and those charges hop between defect sites in the membrane, these trap sites in the membrane, and propagate through this. So it's a form of trap-assisted tunneling, and they tunnel through these traps. Here, because it's an insulating material, the current is highly localized on these hot spots in the membrane. If you had a conducting material, you would expect the current to be uniform. But here you've got a few spots of pre-existing dangling bonds and broken bonds in the membrane that create these initial hotspots where the current can leak. And if you sustain that electric field long enough, what happens is you're going to start generating more and more defects in one of those hotspots, because there's always a probability for those charges that go through the membrane to hit an atom and actually create more defect. And up to a point where you essentially generate enough defect that you have a conductive path, and that's your breakdown event. It's your catastrophic breakdown event. And you see it as in blue here on the right is your leakage current, and you can see how it increases suddenly at the onset of pore fabrication. And depending on how quickly you turn off the voltage, you can basically form a small or larger hole that way. And so the fabrication stops automatically as soon as you stop the voltage, because this is not a chemical etching system, it's really due to this breakdown.
So that's a look at the case.
What you do once you've got a pore, you go back to applying low voltages. And what you see there now is that at low voltages, the current is no longer zero. You actually see at a few hundred millivolts, you see a current passing. And what's even more interesting is that current is ohmic. You've got this linear IV curve. And from that ohmic behavior, you can extract the conductance by the slope of this curve. And using the same equation that I showed you before, you can actually use this conductance to extract the pore size if you assume that the pore has a cylindrical geometry, and knowing the membrane thickness. And this, so here we assume a cylindrical pore also because the linear IV curve tells us that the electric field profile inside is symmetric. And so one of the reasons that it's symmetric is potentially because the pore is also uniform in shape. And so to convince you that indeed the cylindrical approximation is valid, we went on and did some TM images to find where those pores are and to do a top view image of these pores. And this was a difficult task because we used 50 by 50 micron membranes, and we're looking here for a nanostructure of a few nanometers on this massive area. And sometimes membranes were much bigger. And so this is really looking for a needle in a haystack. So we got an image. One graduate student was patient enough to find one, and you can see here that it is quite circular opening of these pores. But to get more statistics, what we did is we locally thinned the membrane using ion beam locally thin membranes. And then we used that ability to have a contrast in the image to more easily find the thin region. And we also did some more fabrications. And here I'll tell you in the next slide how we localize pore fabrication in these locally thin membranes. But we basically showed that on average, we have really nice circular pores opening this way. And so the mechanism by which we can localize pores by locally thinning is due to this phenomenon. So imagine that, look at this figure now. We have the average time to pore creation, or the average time to breakdown, plotted as a function of the applied voltage, or as a function of the electric field. And what you see is this linear behavior on a semi-log plot. So what you have is that the time to breakdown, or the time to pore fabrication, is exponentially related to the electric field strength. So on a given membrane, if somewhere on the membrane it's half as thick, for the given electric potential that you're applying across it, that thin region will have double the electric field strength. And double the electric field strength means much more rapid pore fabrication. So the likelihood of forming the pore on that area is going to be much bigger. Something also that's interesting is that you might have guessed that the breakdown mechanism is a stochastic process. And so here you see the distribution of fabrication time. And if you plot it in a particular way, you can show that it actually follows sort of Weibull statistics, sort of the failure mode statistics, which comes down to being a weakest link problem. But as you can see from this figure of the distribution of fabrication time of the pore under identical conditions, you can see that some pores form quite rapidly, tens or hundreds of seconds, but other pores take much longer. And to tackle that, what we did afterwards is, in software, we simply ramp the voltage as opposed to apply constant voltage to make pores. And here you see in red the voltage that we're ramping, and in black you see the leakage current through our membrane. And we make pores this way to ensure that even if we have varying changes in the membrane thickness, we can consistently make pores under a short amount of time. So that's all well and good, and this is how, by using dielectric breakdown, we make pores. But if it's not of the right size after you've made it, you're going to need to tune its size and enlarge it to bring it to your desired size. And this could be because you're interested in studying a protein molecule that is bigger, and you need to bring it to maybe 5-6 nanometers if it was initially just 2 or 3 nanometers. And here, the physics of enlargement is slightly different. While the fabrication was dependent on the electric field strength on this dielectric breakdown process, the enlargement that we're going to talk about now is related to the amount of ionic current passing through the pore, so on the current passing through the pore. And so to grow the pore while avoiding making others, what we usually do is simply reduce the applied voltage and do a series of voltage pulses to grow the pore. The symmetric voltage pulses to grow the pore in a symmetric fashion. So on the figure on the right, what you see here is a series of 5 voltage pulses in red, and you see that the initial pore size was 4.6 nanometers, and after these 5 pulses, we brought the pore to 4.9 nanometers. And so what I want to emphasize here is that we really controllably brought this pore from 4.6 to 4.9, so a 3 angstrom difference in size in a very controlled fashion. And there's not a lot of fabrication technique out there that can really do that, especially in situ in this environment where you're going to use the pore. And so you can use that very well and bring any pore size that you have initially, let's say a 1.9 nanometer pore, and grow that pore to be of the size that you want. And then we skip this slide, but you can also bring any distribution of pore sizes and bring them all to the exact pore sizes that you want with a really high level of precision. So that was really exciting, and that method really opens up a number of applications that we can do in the lab with these pores, with these precisely sized pores that we make. And we've developed a number of applications in biosensing, detecting different biomarkers indicative of disease, whether it's a protein or a piece of RNA, and digitally counting them to measure their concentration in samples. We've also built advanced nanopore devices that have here a nanopore that has a nanofilter on top that allows us to remove the entropy out of the polymer and stretch the polymer before its entry into the pore and to get
Not well at the moment.
more accurate.
No, I'm fine.
Sorry about that. We get more accurate measurements of the translocation time. We also use pores to play with proteins and characterize them and apply, like confine them in the pore and apply electric forces to unfold them. So besides the biophysical techniques and the biosensing applications of these pores, I want to also emphasize that this controlled breakdown approach is also a very versatile method of fabricating because dielectric breakdown it's universal, and so it's going to work on many materials. So in fact, we've made this work on different kinds of oxides, and some colleagues have shown that you can use it to make pores in 2D materials. So here's an image of molybdenum disulfide nanopore made using similar technique. With a colleague here at the University of Ottawa, Michel Godin, we were able to show that because you don't need direct line of sight anymore with a beam of energetic particles to create a pore, you can encapsulate your membrane with your fluidic channels, and after the fact, by simply connecting and controlling the potentials inside those channels, make the pores when you're ready to use it. Others in the field have shown that you can also pre-align, self-align nanopores with nanostructures on the membrane. Here on the right is a plasmonic structure, this bow tie antenna. And the hotspot of the plasmonic structure enhances pore fabrication right at the middle, and you can really make otherwise complicated structure in a simple way. We've shown that we can also make pores in multiple types of materials, and here are metal dielectric stacks. And so you can think of advanced devices that have nanoelectrodes, for instance, or zero-mode waveguides can be made with this technique. Other groups have also shown that you can, if you use a conductive tip to control the electric field lines, you can locally, you can make an array of pores on a single membrane that way. This was quite an interesting demonstration. But what we wanted to do in my lab was really to find a way to take full advantage of all this this method and really make something easy to use and democratize the field and give it access to a lot of people. And so we engineered an easy to use fluidic cell where we can easily mount the membrane in which we want to make a pore, and have an instrument that's fully automated in software where you can simply type the pore size that you desire with sub-nanometer precision, and the software basically runs through the whole process and gives you the pore that you want for your desired experiment. And so I really believe that we've now really democratized the field of solid state nanopores and allow non-physicists and other researchers, not people with no nanofabrication background, to enter this field, because now they don't need to have this complex knowledge of nanofabrication or use these complicated tools. They can, within minutes, make nanopores and be specialized in focusing on the development of applications on these pores. And this is a very different workflow than what it used to be, when you had to book a TEM, work in the vacuum system, then bring back into the lab your chip and trying to wet them using some chemical treatment before you could do an experiment. And a testament of how easy it is to actually make a pore using our approach is that for a few years we've been running these nanopore workshops, and this was pre-pandemic time. But at the University of Ottawa mini courses, we had outreach activities where we had middle to high school students that came for a week, and we had them for a day, where in the morning we would teach them about nanopores, and in the afternoon we would it would be a hands-on workshop where they would mount membranes and they would make nanopores by controlled breakdown and use them to pass and sense DNA. And it was really exciting to see those kids being so excited about nanoscience and about single molecule detection like that. So I hope we can again do these activities. And many labs around the world, many colleagues around the world have been contacting me as well to try to set up this technique in their lab. And we've published papers describing the method and even providing free protocols and software. But there was really a push from the community to get this a turnkey solution. And so with graduate students from my lab, we spun out a company about 1.5 years ago to commercialize this technology. And we've been offering this sort of complete nanopore in a box solution where you can make pores easy to use and run the type of different experiments that you want, and even provide analysis software and do a lot of customizations in response to the crazy ideas that all the scientists have around the world. And it's been a fantastic experience because compared to my normal academic activities, I've now been able to interact with a lot of researchers around the world and talk to them about their research in a very different context, and seeing academic labs, government labs, and even industry labs use our technology is really exciting and really rewarding as well. And so I think the future is bright for our technology right now. There's a lot of cool applications that are being developed. And it's a really fascinating way to see your research progress that way. And so with that, I need to acknowledge again the amazing contribution of this really talented group of people. In pink here are the people that are still present in my lab today. And the other people on the right are my current lab members, and they're all doing exciting work. I want to thank some funding agencies, because to do this work from discovery of doing something fundamental and doing a discovery to actually translating it to an application requires special funding sources, and NSERC and OCI have been key to enabling this. Thank you very much.